Welcome to the Week 10 guided practice for Chapter 12, Deploying Machine Learning Models. In this activity, we will train a fictional printer maintenance classifier and connect it to a simple client interface. Everything will run inside Google Colab. We will not open a network port or create a public URL. Instead, Flask's test client will simulate API requests inside the notebook, and a Colab callback will connect an HTML form to the Flask prediction route. We will complete the unanswered notebook one section at a time and finish by entering printer measurements into the HTML client. The activity combines machine learning and a small amount of application development. We will train a pipeline containing standard scalar and logistic regression. We will evaluate it, save it, reload it, and place it behind a Flask route. The HTML form does not communicate with a public server. JavaScript calls a registered Python callback in the active Colab runtime. That callback sends a JSON request to the Flask application through the test client and returns the API response to the page. This gives us a simple deployment demonstration while avoiding tunnels, background servers, ports, and CORS configuration. Begin by installing Flask. Google Colab already includes most of the data science libraries used in this notebook, but this command ensures that the web framework is available. The quiet option reduces installation output. If Colab asks you to restart the runtime after changing a package, follow the message and rerun the notebook from the beginning. Import pickle and path for model persistence and file handling. NumPy creates the fictional dataset, Pandas manages the table, and Matplot creates the charts. From Flask, import the application class, JSONify, and the request object. The scikit-learn imports include logistic regression, the evaluation metrics, the train test split, pipeline, and standard scalar. Run the cell and confirm that the library is imported successfully. The dataset generation cell creates 240 fictional printer records. The features include weekly pages, paper jams, toner percentage uptime, and warning events. A hidden risk expression is used only to generate the fictional target name need service. The model will not receive the hidden formula. 6 feature values are replaced with missing values so we can practice a basic cleaning step. Run the cell and verify that the data set has 240 rows and 6 columns. Before training, inspect the data set, display its shape, count missing values, examine the target class counts, and review numerical summary statistics. The missing value output identifies 6 incomplete feature values. The target counts help us determine whether both classes are sufficiently represented. The summary statistics provide the range and distribution of the printer measurements. Inspection should always occur before cleaning or modeling. Calculate the target counts with value counts and sort the index so class 0 appears before class 1. The bar chart shows the number of printers in each target category. Class 0 means no immediate service recommendation, while class 1 means service is recommended by the fictional target. The classes are sufficiently represented for this classroom exercise. For this guided demonstration, remove rows containing missing values with Dropna. The copy prevents later assignments from modifying a view of the original data frame. The original data set contains 240 rows, and the clean data set contains 234. The final missing value count should be 0. A real project would also evaluate whether deleting incomplete records could distort the data. Create the feature metrics using the 5 printer measurements. Create Y from the need service target. Use a 75% training and 25% testing split. The random state makes the result reproducible. Stratification preserves approximately the same class proportions in both subsets. The test data remains separate until evaluation. Create a scikit-learn pipeline with 2 steps. Standard scalar standardizes the numerical features. Logistic regression performs binary classification. Keeping the 2 steps together ensures that the fitted scalar is applied consistently during testing and future predictions. Fit the pipeline using only the training data. The pipeline is now ready for evaluation. Generate predictions for the untouched test data. Calculate accuracy and the confusion matrix using the true and predicted labels. The expected accuracy is approximately 0.8, although small differences may occur if library behavior changes. The classification report provides precision, recall, and F1 score for both classes. The confusion matrix display makes the correct and incorrect predictions easier to interpret. A false negative would mean the model failed to recommend service for a printer whose target indicates that service is needed. Create a path for the model artifact. Open it in binary write mode and save the complete fitted pipeline with pickle.up. Then open the same trusted file in binary read mode and reload it with pickle.load. we save the full pipeline rather than only the classifier, because the fitted scaler is part of the prediction process. Never load a pickle artifact from an untrusted source because loading can execute arbitrary code. Create the Flask application and enable testing mode. Testing mode helps errors surface while we work through the notebook. Store a model name and version that can be returned by the API. We are not starting Flask's development server. The application will be queried directly using its test client. Add a getRoot at health. The function returns a dictionary containing the service status, model name, and version. Flask converts the dictionary into a JSON response. The health root gives clients a simple way to confirm that the application is responding before they submit prediction data. Add a post root at printer pref v1 predict. Read the JSON body with request.getJSON. If the body is not a JSON object, return a structural error with HTTP status 400. Next, compare the incoming keys with the required feature names. If any fields are missing, return the error message and the missing field list. The model should not receive incomplete input. Inside the try block, convert each submitted value to a float. Create a one-row data frame using the same feature names and order used during training. The except block catches values that cannot be converted to numbers and returns another 400 response. Using a data frame preserves feature names and makes the API input compatible with the saved pipeline. Call the reloaded models predict method and convert the return class to a standard Python integer. Call predict.proba to obtain the class probabilities. Select the value associated with the return class and use it as the confidence shown by the demonstration. Create a readable label and return the prediction, label, confidence, model version, and disclaimer as JSON. The result supports technician review, it does not replace it. Create the Flask test client inside a with block and issue a GET request to /health. The test client constructs the request without starting a server or opening a port. The expected status is 200, and the response should contain the model name, version, and an OK status. This confirms that the Flask root is available inside the notebook. The provided record describes a high-usage printer with low toner, several paper jams, long uptime, and many warnings. Submit it to the prediction endpoint as JSON. The test client automatically sets the JSON content type. The expected status is 200. The response should include the service label, the return confidence, the model version, and the educational use disclaimer. The incomplete request contains only 2 of the required 5 features. Submit it to the same endpoint. The API should reject the request with status 400 and return a list of the missing fields. This demonstrates why input validation belongs inside the server rather than relying entirely on the client interface. The second invalid request includes all required fields, but the weekly page value contains text instead of a number. The float conversion fails, and the API returns status 400 with a numerical value error message. Testing both valid and invalid requests confirms that multiple branches of the endpoint behave as intended. The HTML page needs a bridge to Python code running in the Colab kernel. Define a callback that receives the 5 form values and creates a JSON payload. The callback calls the Flask prediction route through the test client and returns the status code and JSON result. Register the callback with the name printer.print.predict. The JavaScript in the next cell must use this exact name. If the runtime restarts, rerun this cell before using the form again. The HTML client is provided so the activity remains focused on the deployment workflow rather than front-end development. The page contains 5 numerical inputs and 1 prediction button. When the button is selected, JavaScript calls google.colab.kenlab function using the registered callback name. The return API result is displayed as a readable card and as formatted raw JSON. This form exists only in the current notebook output and active Colab runtime. Use the default values and select predict maintenance need. The page sends the values to the Colab callback. The callback sends a post request to the Flask route through the test client. The route validates the values, creates the model input, runs the save pipeline, and returns JSON. The client displays the service recommendation and confidence in the return class. Now replace the values with a lower usage printer, 2000 weekly pages, 1 jam, 82% toner, 12 uptime days, and 0 warnings. Submit the form again and compare the new result. The final reflection connects the machine learning and application concepts. Training learns model behavior from historical examples, while inference applies the fitted pipeline to new observations. Saving the full pipeline preserves both preprocessing and classification. The Flask endpoint receives JSON and returns structured JSON results or error messages. The test client works without a server because it calls the Flask application directly inside the Python process. The Collab callback connects browser JavaScript with that Python process. A production service will still require authentication, HTTPS, stronger validation, secure artifact storage, a production server, logging, monitoring, privacy controls, versioning, rollback, and human oversight. Save the completed notebook with your name and verify every submission item before uploading it.